In this video, we're going to learn about a systematic way of naming organic molecules. This is a complement to our ability to now draw these organic molecules and to indicate structure. So the problem kind of comes from the fact that we can't just give every single molecule a unique name, because then there would be so many hundreds of thousands of names that no chemist could possibly memorize all of them and know exactly what structure each name refers to. When this problem arose historically, people started to come up with what is called an IUPAC nomenclature system, IUPAC nomenclature. It turns out now this nomenclature system takes up about an entire book's worth of instructions. And so what we're going to do is try to distill that down into the most important pieces. So let's start off looking at a molecule of aspirin. So again, this name aspirin is just a name that someone gave historically. We know it refers to this line angle drawing. But if we're talking about more of a nomenclature in written form, the name of aspirin should be like this. So 2-acetoxy-benzoic acid. And so these names are systematic, and they are created in a way such that you can create the line angle drawing given the name, and you can take a line angle drawing and convert it into a name. And so what the IUPAC nomenclature does is it tries to break out these common groupings of atoms within molecules and help you identify those. And so it turns out if you look at this here, you can find the various pieces. So the benz in the middle is kind of the first piece that I noticed. That's the benzene ring right there. The pink oic acid at the end refers to this piece right there. The 2-acetoxy at the beginning refers to the fact that there's this type of a group here, and that it is not at the 1 carbon the pink group is attached to, but rather at the 2 carbon, so kind of 1 away. And so with all those pieces, you're supposed to be able to create either a line angle drawing from the name or a name from the line angle drawing. One more concept that will help us as we keep going here is that these common groupings of atoms that show up in a lot of different molecules, these are called functional groups. And so these are important because even in different molecules, these functional groups will kind of behave in a certain way that we can predict and kind of give certain properties to the molecule that we can predict. So I had mentioned that the IUPAC nomenclature book is really, really long. So I have kind of put together a short guide here, so I'm going to pull it up on the screen real quick. So this is a brief guide to IUPAC nomenclature. You can also find this in booklet form here, so I'll keep that camera there, just so you know. So this is a single page that's meant to summarize, I would say, 99% of what you need to know to be able to do all of IUPAC nomenclature. And so if you're looking at this brief guide right here, what you'll see at the top is in this box right here is the general kind of scheme of how the nomenclature is come up with. There's only really 4 pieces to it. There's a stereochemical indicator, which we will get to later videos. There's this prefix component, there's a root, and then there's a suffix. And so our job is to be able to figure out what the prefix, the root, and the suffix are. And so you can kind of see in the color coding here that you would follow and figure all of this out following the steps here. And so we'll start with figuring out or talking about the root of the molecule, or what is called the parent framework. And so what I think of when I think of parent framework is, what are the carbon atoms? What do they look like in the molecule? They make up the backbone of the organic molecule, so what are they looking like? And there's really 2 kind of different general ways we can think of the carbon atoms. They can be organized into nice chains, or they can be organized into rings. So when it comes to chains, there's a pretty simple system. We kind of have prefixes for different chain lengths. So if the chain has 1 carbon, we would call it a meth something. If it had 5 carbons, we would use pent in front and then some suffix at the end here. The suffixes depend on the types of bonds that are in that chain. So if there are only single bonds, that's called an alkane, and so we would use a suffix of ane here, A-N-E. If there's a double bond, we would go with ene, E-N-E, and if there's a triple bond, we would go with yne, Y-N-E. So let me give you an example here. So if you have this molecule, and I asked you to give an IUPAC name for this molecule, you would go through and figure out what the parent framework is, and you would count 1, 2, 3, 4 carbons. That would take you to the bute prefix. You would see there's only single bonds, so then you would pick an ane suffix, and so this molecule is butane. So then the other way around, I could start with a molecule name, so let's say hexene, and ask you to draw what that molecule looks like. Same idea. So you see the hex, there's 6 carbons, so you draw a 6-carbon chain. And then the ene tells you there's a double bond, but it doesn't tell you where there is a double bond. So for now, I'm just going to stick a double bond in here arbitrarily. But it is the case that you could draw another molecule that looks like this. That would also be hexene. Right? And so the point of giving you an example like this is to show that the specificity with which you speak can make a big difference on what someone else interprets. Right? So if I say hexene, the listener doesn't know if I'm talking about this molecule or that molecule. Okay, we'll leave that there for now. Move on to rings. And so there's kind of within rings a couple of different situations. So the first is just kind of taking a chain of atoms like this and kind of folding it around and bonding it together to make a ring. Right? And so when that happens, we give this whole business a prefix of cyclo. So 4 carbons together would be a cyclobutane. A molecule like this one has 6 carbons in a ring, so that means that we start with cyclo. There's 6 carbons, so we do hex, and there is a double bond, so we can do ene, and that's cyclohexene. The challenge with rings is that many rings do have their own unique specific names. One special case is in aromatic molecules. We're going to talk about aromaticity in a future video, but for now just agree with me that a molecule like this one, so a 6-membered ring with 3 double bonds in that ring like so, that's called a benzene, and everything nomenclature-wise will just use benzene as kind of the parent framework of the nomenclature. So again, many rings do have unique names, and it's basically impossible to memorize all of them, but luckily there are plenty of resources that you can go to that give you tables of different rings by how many kind of atoms are in the ring, and then also what types of elements are in the ring. Alright, we just talked about the parent framework. The other big piece, which is identified in step 1 here, is looking for the principal functional group, or even just functional groups in general. Right? So the way this works is that there's a ranking of functional groups. That ranking is provided to you right here in this table. This ranking roughly follows what's called the oxidation level of the functional group, which means that lower oxidation level functional groups tend to be lower ranked. Higher oxidation level functional groups are higher ranked. The way you figure out what oxidation level is just looking at a functional group is to count the number of non-carbon or hydrogen atoms that are bonded to the carbon in the functional group. When we say non-carbon or hydrogen atoms, that is often also stated as this word, hetero atoms. So in a functional group, we find the carbon atom and then we count how many bonds there are to hetero atoms. So I'll give you an example here of 3 different functional groups. So the functional group would refer to kind of this part of the molecule. And so if you're looking at this, you can see there's a carbon here. This carbon has 3 bonds to oxygens. This has 2 bonds to oxygens. This has 1 bond to an oxygen. So I have these ranked from high to low in terms of their functional group ranking. And so every functional group then in this table here has its own prefix and suffix. So when it's the highest ranked functional group in a molecule, we use its suffix. When it's not the highest ranked, we would use its prefix. Okay. And so just to show you what these are here, you can go through and find these on the table on your own time, but this is a carboxylic acid, and so this is the suffix and that's the prefix you would use. This is an aldehyde functional group with these characteristics, and this is an alcohol with these suffixes and prefixes. So it may seem a little bit daunting to figure out what all the functional groups are. That is definitely something that becomes memorized as you are more familiar with the material. But to start off, again, there are nice there's a nice kind of table of functional groups here. So what you can kind of see here is these are the most common functional groups you'll encounter in organic chemistry, sorted by oxidation level from first, second, third, fourth. And then also within that subcategorized by whether there's kind of a nitrogen atom involved, a phosphorus atom, an oxygen atom, so on and so forth. So given a new functional group, you would turn to this table, try to figure out which category you're in, and then you'd be able to find the name that way. Okay, I want to take a small detour here to talk about what are known as modifiers. Modifiers are really valuable for when we're kind of verbally or talking about a functional group, right? So when I don't want to say the entire IUPAC name of a molecule, but I just want to give a little bit of context, then I'll use a modifier. So one important thing that you'll get used to using is this idea of taking the prefix for a functional group and just adding a YL at the end, so an IL at the end. I think this is best shown through example. So here I have 3 different groups attached to a benzene ring, right? So if I was trying to talk about this molecule, I could say, oh, hey, look at this chain at the top here. That's an ethyl group because it is 2 carbons long. So eth plus YL, that's an ethyl group. The 6-membered ring at the bottom right here, this would be a cyclohexyl group. And then this 3-carbon chain right here would be a propenyl group with the EN in there to kind of confirm that there's a double bond. A second type of modifier that shows up very often is a word in front of the name of the functional group. And it also is trying to show you context, but it is trying to tell you what the functional group is attached to. Right? So in the first case, this case didn't really give you much information about what the ethyl group is attached to, just that it is an ethyl group. Second case down here is trying to give you that context. So functional groups can be attached to chains. So if it's like this right here, this is called an alkyl functional group, and specifically it's an alkyl amine because it's attached to an alkane chain right here. If it's attached to a double bond directly, then that falls under a vinyl category. So now I would call this one, for example, a vinyl alcohol. If that double bond the functional group is directly attached to as part of this so-called aromatic ring, then we would use the word aryl here to kind of indicate that it's an aromatic ring that's attached. So this is an aryl bromide. When there's kind of a skip, so there's a double bond, but then 1 carbon between the double bond and the functional group, that is called an allyl situation. So this is an allyl alcohol. And again, for benzene, we have this unique situation where if there's a kind of a CH2 between the functional group and the ring, that's a benzyl alcohol. When we're dealing with alkyl situations, there's a little bit more context that people will like to provide, and that is this idea of primary, secondary, and tertiary. And what that is referring to is how many other carbons is this carbon atom attached to. So for example, this alkyl alcohol has 1 other carbon attached to the carbon right here, so it's a primary alcohol. There's 2 carbons here attached to this carbon, secondary alcohol. 3 carbons here, tertiary alcohol. A caveat to this system of referring to things is that nitrogen-containing functional groups are going to use primary, secondary, and tertiary to refer to the nitrogen atom rather than the carbon atom. So this is a primary amine, this is a secondary amine, this is a tertiary amine. Alright, with all of that kind of really quickly thrown at you, I'm going to go through 2 examples here of providing an IUPAC name for a given line angle drawing. So the first one we'll look at is an amino acid called glycine. So this is the simplest amino acid. Its line angle structure is shown there. And so flip back here to the guide. And kind of walk you through the whole process. All right, first we want to figure out in step 1, what is the principal functional group? To figure that out, you need to first figure out what functional groups are even there in the first place. Right? So if you're looking at this molecule, typically you'll want to look for heteroatoms. And when you do that, you should hopefully notice that there are kind of that set of situation and then this one right here. Right? So 2 different functional groups. You'll find that these are an amine and a carboxylic acid. And if you go look at the functional group ranking right here, you would find in the table that carboxylic acid is at the very top. It's the most highly ranked. And amines are here, so not very highly ranked. So then our principal functional group is the carboxylic acid. You could also make that judgment just by noticing that this carbon has 3 bonds to heteroatoms. This carbon only has 1. The next thing we want to do is figure out what the framework is. And so the framework was that carbon chain. And so if we're looking at this chain, we would start from the carboxylic acid carbon, so that's 1 carbon, and then there's only 1 other carbon. So there's 2 carbons total. And so then we would start with this ethan situation for the kind of framework part of the name, the root part of the name, with the "and" there because there's only single bonds between carbons. Right. The next step is to get our correct suffix. So to get the suffix, I would go to my table here, look under suffix, replace the E from the ethane, so really I have ethan, with kind of this top piece, ethanoic acid. If you're looking at this, you'll notice that the carboxylic acid has 2 different possibilities here, 2 different suffixes that are used in different cases. So these are dependent on whether the carbon atom of the carboxylic acid is part of the framework or not. So in this case, it is part of the framework, so we use the one with the parentheses on it. That's the oic acid suffix. So I go ahead and put all of that together. I have the amino group attached to the second carbon, so that's 2-amino and then ethanoic acid. That's the name for the molecule. Okay, now I'm going to give you a more complicated one, also amino acid. So this right here is the amino acid tyrosine. So you kind of see it looks structurally similar to glycine, but there's a little bit more going on, of course. So same steps, right? So I go through, look for my principal functional group. I find that it is still a carboxylic acid right here. Right? So I have that functional group. I also have the amine, and then I also have an alcohol at the top right here. Now my framework is a 3-carbon chain because I have to start from where the principal functional group is. So that's 1, 2, 3. Labeled like that. We already talked about what our suffix will be. This is the same as the previous example. Where things get complicated is in the prefixes to the entire name. So like glycine, there is an amine group at the second carbon that gets us to 2-amino. The part we have to account for now is that at the 3 carbon, there's this extra business right here. So there is an alcohol, but the alcohol itself is not directly attached to the 3 carbon. There's a benzene ring between them. Right? So it's almost like there's a separate kind of a nomenclature problem here. We haven't accounted for all the carbons yet. And so the way this works is to take the 3 and say that I can't just call this, it's not 3 whatever alcohol, but it's rather a more complex problem. So I do a 3 and then I hyphen and then open a parentheses. And then within that, I treat this piece as a separate nomenclature problem in which I can number the principal functional group as being at that location where that benzene ring is attached. And then if I number outward, then I get to 4. So that there's a alcohol at the 4 position on this benzene ring. This benzene ring, for what it's called, you can go into this table here and find that it is down here, and it has this prefix phenyl, P-H-E-N-Y-L. And so that's what we would use as the kind of mini root. So that's the root of this separate nomenclature situation down here. So there. I'll stick kind of a phenyl in here. And then on that phenyl ring, there is a 4-hydroxy functional group. And that kind of closes the whole thing off. And so that tells us that, again, in total, we can come up with this name, a propanoic acid that at the 2 position has an amino group, and at the 3 position has a 4-hydroxy phenyl group attached.